All right, let me try another video solution, especially now that we are in some really hard material. Chapter 30, number 37, looks like a good one to do here now. Maybe I better put page 1. This might take a couple pages. But it says here, a single turn square loop of wire, 2 centimeters on each side, carries a clockwise current of 0.2 amps. The loop is inside a solenoid with the plane of the loop perpendicular to the magnetic field of the solenoid. Okay, I'll stop there. Let me kind of make a solenoid, and maybe I'll try to draw the interior part of the solenoid. And so maybe here's the interior part. And let me start with the wire here in the solenoid. It says the solenoid, let's see what it says, the loop inside the plane perpendicular. Which way is the current in the solenoid? The solenoid carries a current clockwise. So if I was standing over here on this edge, looking in, and a wire came up and went over, and so the back side, then wrapped around, went over the top, round over the top, and then back. They're saying the current would go clockwise, so that means it would climb up this edge, go over the top, go down on the back edge, and so this is the direction of the current, and so maybe a battery or something would be hooked, something like that. Now, I did all that first because we need to know which way the magnetic field is, I suppose. Let's see. They gave us direction. So the magnetic field then, and usually written in green here, and so let me figure that out and give this as an opportunity to use what I keep calling right-hand rule number 2. And let me say it again, don't confuse it with the right-hand rule that we do a cross product with, where we, put our fingers in the direction of the first one. The second one is where we hold our hand with a right hand and we look at our currents. And if our currents are straight, well, we'll use our thumb to represent the current. If our currents are curved and loopy, then we'll use our fingers. And that's what we have here for a solenoid. Our current is loops. And so I'm going to use my fingers for the current, and then my thumb will give me the field. All right, so I need to adjust my right hand now so that my fingers are in the direction of the current. Okay, so I guess they would loop away like this. And so here's my fingers kind of curling around with my thumb pointing down the axis of the solenoid. So I'll try to draw in green. Uh-oh, probably drew too many green now because I got to get that square loop in there somewhere. Okay, but there is, and I guess it would flare out at the end. So there is kind of what the magnetic field looks like. In fact, let me take this as an opportunity then. One of the results of Ampere's law was to show that the neat thing about this design of a solenoid is it would make a very strong and uniform magnetic field, and that's why we like this design. This and toroids make really nice fields. Now, the toroid does not make a uniform field, although it does make a very strong field. The solenoid here makes a uniform field, or at least the ideal case of an infinitely long, tightly wound. We have a problem actually here in chapter 30 where they give it a finite length and you have to add up a bunch of loops. I forget what number that was. That's, maybe I can even see it up here on the assignment. Long, tightly bundled. Well, I don't see it at the moment, but that one was to show that at the end, the of a finite size solenoid, the field is half as strong as this ideal one. All right, so I'm going to go with the ideal one, or maybe put another one as it's long and it's skinny, and what my experiment or the loop is actually kind of in the center. So the field is probably something very close to that. So maybe not ideal, but very close to that. So the mu naught is this 4 pi times 10 to the minus 7. That's the I always got to double check how I say this, because there's the permittivity of free space. That's for electric field, and this is the permeability of free space. So this is the magnetic field. And then the little n is the number of turns per meter, or per length here. And so if I continue to read this one, it says the solenoid has 30 turns per centimeter. So I'm going to write that as 30 turns per centimeter, but I'm going to write it as per meter and put in the 0.01 meters. Oh, and I guess I should have put in my units here for the permeability of free space. And so that's a Tesla times a meter over an amp. And at this point, you can see how the meter upstairs and the meter downstairs are going to cancel. And the last one is the I. What is the current here? And so what did I read here? That the solenoid has 30 turns per centimeter and carries a clockwise current of 15 amps. And so the amps are going to cancel off. And so, not a surprise, we end up with the unit of Tesla for the strength of the magnetic field. All right, so this is 4 times pi times 1 times 10 to the negative 7 times a 30 and divided by a 0.01, and then finally times a 15, and I get a 0.0565 Tesla. Whoops, I did it twice now. Tesla for the strength of the magnetic field. And in my picture, then, it would be going in the negative x direction. All right, so that's part of the problem, is just realizing that we have a solenoid and how do we get the magnetic field, and that it's a uniform magnetic field. The other part of this, then, is to find the force and the torque, and that really goes back a chapter. So both of the chapter 29, we learned how to get a force on a wire and also a torque. So I'll do the force first. That's kind of normal, and then the torque, although I think calculating the torque is probably easier. But let's see if I can draw the loop. And now that I kind of drew on here, I wonder if a different color would stand out. Oh, I don't think I've ever used this dark purple color here. So maybe I'll give this a try. And so in here, there's a loop. And if you read it carefully, it says the loop, let's see, single turn square loop of wire, 2 centimeters on its side, and carries a current also clockwise in a point at 0.2 amps. The loop is inside the solenoid with the plane of the loop, here's the key, perpendicular to the magnetic field. Okay, so the plane is perpendicular. All right, so let's see. So the field is going this way. So let me grab a little sticky in there. Maybe you can see it a little better here. But if this is the solenoid and this post-it note is my square, then it would be in here like this, so that the plane is perpendicular to the field. See, the field is going in the negative x direction, and the plane is perpendicular to that. What axis would that be? I guess that would be the ZY plane. Okay. So imagine that. I'll try to draw it, and I wanted to show you in more 3D because I'm not going to do a very good job of drawing it, but I'll draw this straight edge. That'll be this top one, and then this top goes back and the bottom goes back, so I'll kind of do this at an angle. So that'll be kind of like the z-axis, and then the bottom here would look something like that, and then the currents would be going in a clockwise direction. So on this top edge would be going up, and on this, well, I don't know, I shouldn't call it the top. The edge closest to the camera here would go up, and then this edge, I'll call that one the top, would go in to the paper, and then this back edge here would go down and then out again, so that this person standing over here on the side can look and see it go in the same direction, a clockwise direction. Okay, now the reason I said this takes us back a chapter is because we learned that for a straight wire, the force on a wire in a magnetic field would be given by this equation, where this is the current in the wire, this is the length and the direction of the wire, then it is crossed with the strength of the magnetic field. And so that's this right here. So we did that. So let me just do the magnitude of the force for a second. I won't worry about direction quite yet. That would just be the current, and then the length of the wire, then the field, and then the sine of the angle between them. And let me do this one here that is closest to the camera. Let me call that number 1, okay? And then as long as I'm labeling them, this top one up here, then let me call that number 2 current, and then this backside edge number 3, and then number 4 as we go all around the square that is inside of our solenoid. Okay, so this I would be the current in this little square, not to be confused with this 15 amps, which is the current in the solenoid that's producing the field. So that current is taken into account right here. What is the strength of the field? But this is the current that is in this wire. And so that's probably the maybe more complicated thing about integrating last chapter with this chapter, is that we've got this current in this equation, but which is it? Because we've got two. We've got a current in the solenoid and a current in the square loop. And this, of course, was the current of the wire that we're trying to find that force on. So it would be this one in purple, whereas then the magnetic field, see, in last chapter we just said, oh, there is a magnetic field. We didn't really say where it came from, but that's why this chapter, which is the source of the magnetic fields, is telling us, well, these magnetic fields come from currents, and so that would be this one here. So I want for this current, the current that is in this square loop, and so they said this was 0.2 amps for the current that is in that square loop. And let me just double check that. Yeah, and a clockwise current of 0.1. Okay, now L is the length, and they said it was 2 centimeters long. I'll write it in meters. And again, I'm not doing the whole square yet. That's ultimately the question. What is the force? It actually says what's the force on each side of the square. So this is 1/4 of the problem, and I'm just number 1 here. The field, well, that's why I did that a little earlier, was to figure out what the field is, and that would be in Tesla. And maybe it'd be a good time to pause and to remember that Tesla is a Newton that you would get on 1 coulomb of charge moving at 1 meter per second, which you could then do it a little different and put the coulomb per second together and call that an amp and a meter on the bottom, because the amp on top and the meter on top would cancel with the amp on bottom and the meter on bottom to give you a force in newtons, which is perfect. That's the right units here. All right, so grabbing the calculator, I already got the magnetic field from my last little calculation, and so 0.02 for its length and 0.2 for the current comes up with 2.26 times 10 to the -4 newtons as the force on this little piece. Okay, so if that's the force, or at least that's the magnitude of the force, I should say, what is the direction of it is another piece of this. And so this is where I got to do the right-hand rule with a cross product, okay? So I'm going to do the first right-hand rule, not the one I did earlier where I figured out the direction of the magnetic field in the solenoid, but the first one. I got a cross product to figure out which direction is the force. And so we put our fingers in the direction of the first vector, which is the L, which is the direction of the current. And so in my picture, that's up. Then we have to kind of move and rotate our wrists, always leaving our fingers up in the direction of the first one, so that we could close our fingers, or put another way, our palm will be pointing towards the magnetic field, which we said already was in the negative x direction. So it would be best to hold my right hand like this, because it would be going in the direction of the current, and then I'd be closing towards B. And my thumb then would give me the direction. So it looks like it's going in the direction of the camera, towards the camera. And so in my picture, if I tried to draw a force vector, say in a light blue here, if that stands out, looks a lot like the green one, but it would be coming in the z axis here. So this would be the force on the first one. And in fact, as you might suspect, if we go to number 2 here, we're going to have the same magnitude. Everything's going to be the same. Oh, and I forgot to say sine of 90 degrees here, didn't I? I hope you saw that. But the current is going up. That's the y direction. And the field, as we said earlier, is the negative x direction. And those are at 90 degrees to each other. So that's what we put sine of 90 degrees. And I just kind of overlooked it real quick because sine of 90 is 1. And so apologize, I almost didn't point that out. Okay. And then what I was trying to say here is number 2, we really have kind of the same thing. We would look at this and we'd have, well, the same current in it because it's a single loop. So it would be, this wire 2 is in series with wire 1. So it's the same current. It's a square, so it's the same length. It's in a solenoid, and the solenoid has a uniform field everywhere. So the field would be the same everywhere. And it still is 90 degrees. Now, you might say it's a different 90 degrees because the current's going back. So you might say the negative k direction. All right, and the field is in the negative x direction, but that's still 90 degrees here. If I hold this up here, going down and left is 90 degrees. And so they're still at 90 degrees to each other. So everything would be exactly the same. You can see that for 3 and 4. And so if I wrote this maybe as the magnitude of number 1, I could say it's the same as the magnitude of number 2, and the same as the magnitude of number 3, and same as the magnitude of number 4. And so I'm going to get the same magnitude. However, they are not the same directions. And so when we write it as a vector, if you will, F1 is this 2.26 times 10 to the negative 4 newtons. And as I said, in this kind of setting that I have, then this would be in the k hat direction. Whereas if we look at force number 2, as I just said, it would be the same magnitude, okay? But we got to do this right-hand rule again. And again, this is the one for vector cross product. So I'd put my fingers going into the page and then adjust my wrist so I can close towards it, and I get this upward direction. And so there would be the force. I guess that would be a y direction. So maybe we would call it a j hat. And then if we go to number 3, again, we would argue that it's the same magnitude, okay, but what is its direction? And you could actually come back to number 1 and see, well, the direction of the current is the negative of what it was for 1. So if you went through everything, you would just get a negative. So instead of getting a k, I should get a negative k hat. But maybe I should also do my right-hand rule here. The right-hand rule number 1 for vector cross product. So I'd want to put my right hand going down because the current's going down, And I would want to adjust my wrist so that my fingers can close towards the field, which is the negative x direction. And so my thumb is pointing down and or into the paper. I got to be careful here because on your video screen this is down, but into the paper is down in terms of gravity. And I hope I don't say that backwards here. So, but it gives me into the paper. Okay. So as it goes into the paper, that would be the negative z direction. And so 1 and 3 are equal in magnitude, opposite, net force being 0. And then number 4, again, we can do the same argument that 4 is just like number 2, but in the opposite direction of the current. So when we go through this math, we should get the negative of that. So instead of getting a j hat, we would get a negative j hat. But let me also then do this right-hand rule. So I would have be current coming towards the camera, so that'd be this way. So I point my fingers up, and I have to kind of twist my hand around so I can close my fingers towards the field, which is the negative x direction. And see, notice my thumb is pointing on your screen would be down, and so that would be the negative excuse me, j hat direction. And so again, these two added together would give a net force of 0. So the total net force on this, and I don't even think that was asked. They asked for the force on the individual ones. But I'll just add to that the total force then on this loop is 0. So this loop is not going to be pushed left or right or up or down or forward or back. There's a net force of 0 on it. However, and so this is why they asked for the torque, it will tend to rotate. And so that's why this makes a good motor. This is what we talked about in that application sections at the end of chapter 29. This is how you build a motor. You put a loop of wire and you run current through it, and you do that in a magnetic field. Now, when we were talking about this in chapter 29, we did not say where the magnetic field was coming from. But one option would be to make a magnetic field by having these coils of wire. So, to make an electric motor, let's say, a garbage disposal, a vacuum cleaner, the starter motor of your car, the spinning of the hard drive of your computer, the disk drive. The world's just filled with electrical motors. Maybe your car is an electric motor. But they just have a loop of wire in a magnetic field. And it makes a lot of sense to use that same current that's going through this loop of wire, to use that current to also then flow through here first. And so that same current first generates the field, and so that's the solenoid here, and then you put the current running through this loop of wire, and there's going to be a twist to it, a torque. And so I guess I need a second page to complete this problem. And so page 2 is asking us to calculate the torque. And the torque is this mu cross B. At least for a single loop, we'd multiply it by a factor of n if there were more than one loop. But this is a single loop one, so we can get rid of that. And we did some problems like that in chapter 29. And you might remember then the magnetic moment was defined as the current times the area vector. So I'll begin with realizing that I have a cross product to do, and I will just do then the magnitude of the cross product, because that will be the magnitude of mu, the magnitude of B, and the sine of the angle between them. And the magnitude of the mu, the magnetic moment, not to be confused with the permeability of free space, but would be the current times the area, and then times the magnetic field, then times the sine of the angle between them. And maybe the same warning here about this equation for the current as I also gave for the force. If you remember back in chapter 29, this was the current in that loop created by some magnetic field. And in 29, we didn't really say where that came from, so there was never a confusion of which current to use. But in this problem, we have the two currents. So this is the current in the loop, whereas the other current, the 15 amps, is the one that's creating the field. So putting in our numbers again here, this was what, a 0.2 amps. The area is, of course, the size of this, which was what, 0.02 squared, so 0.02 meters squared. And the magnetic field is coming from this solenoid, so 0.0565. And we said earlier Tesla, but then let me just put a Newton over an amp and a meter, so that when I'm all done, the amp will cancel off. One of the meters will cancel off, but not both. So I will be left with the appropriate units for a torque, which is a Newton meter. So grabbing my calculator here, I would have 0.2 times 0.02 squared times 0.0565. And so 4.52 times 10 to the, is that a -6? So pretty small. Got a small loop and really a small amount of current. Well, other than the one current making the field in the solenoid's pretty big, but the other one's kind of on the small side here. But that would then be the torque. Oh, shoot. I did it again. And this is a very serious mistake this time. The sign of the angle. And, okay, well, keep going. But I wish I would have done this before I did the calculation, because I just kind of wasted your time and my time. But what is the direction here? And the direction of the magnetic moment is when you take your fingers, you know, and you curl them. The direction of the magnetic moment is the direction of the field. So if I'm looking at this square and I'm using the second right-hand rule, my fingers, I know they're not square when they fold like this, but whether it's a circle or a square, it's the same idea. They loop around. So I'm going to curl it in the direction of the purple current here, and my finger would point, my thumb would point in the negative x direction. And so I would have a sine of 0 degrees, which is 0. So when you multiply those two together, you get a total torque of 0. And yeah, sorry I didn't, because I almost dropped that sign there. But I was looking at this picture, noticing that, you know, if you pull on a rectangle to the left and then to the right and then the up and the down, there's no twist to it. There's no torque to it. So you can see just from the forces that the torque is going to come out from 0 if we just go back to chapter 10 of Physics 121 here. But anyways, this should give us a 0. And I was like, wait a minute, I didn't get 0. But I did, because I got careless and almost forgot to do that angle. So 0 Newton meters if we want to do the units, and so no torque. This is not in a state of twisting. Now, had, just as finishing up this, the rectangle been in the plane of the paper, then we would have seen, like, let's say I twist it so it looks like this. So here's number 1. This force pulling towards the camera, and this one here pulling back is going to want to twist it back like that. So if you get in there and you turn it this way, you actually have to fight against the magnetic field and put it back in this. And if you let it go, it's going to want to go back to here. In fact, it would probably do something like this. It would go and then go too far, and then the torque would be the other way, and it would kind of kind of oscillate here like a pendulum for a little bit. Friction would wear it out, and eventually would settle down right at this angle if it had the, you know, some bearings here or an axis that it could going to rotate it with. Of course, this would still be up and that would be down. That's not making it do any kind of twist. But so that would be the rotating axis as it would rotate around. All right, well, hope that helps somebody.